welcome to our seminar series, and also everyone online also welcome as well. So we are glad to have today we have Professor Pathak from Indian Institute of Technology, Roorkee, and he's visiting us for this week and coming next week, part of it, and he will give a presentation today, give a lecture on robotic construction. And Professor Pathak, his research areas in robotics, dynamics, and control, as well as fun graph modeling. And he's a professor in the mechanical and industry engineering department at IIT Roorkee since 2006. He has been working on mechatronics for a long time, and he has co-authored a book on Intelligent Mechatronic Systems, Modeling, Control, and Diagnosis, published by Springer in year 2012. He also has several online courses through National Program on Technology Enhanced Learning on mechatronics and modeling and simulation of dynamic systems. These two courses has been very popular. He's a founder of a startup, RoboLife Private Limited, with a startup company. This company works to take robotics products developed in robotics lab to the market. He's a member of ASME and IFToMM committee for multi-body dynamics. So here, welcome Professor Pathak to give the talk today, and please go ahead. Yeah.
Thank you, Professor Lee, for nice introduction. It's my pleasure to be here among all of you. And it's almost vacation time, going to be there. So, yeah. So initially, I'll just talk about my institute, that is IIT Roorkee. Then about my lab, which I am heading, Robotics and Control Lab, and finally my presentation of the day, which is based on our collaboration with Professor Laila and Professor Lee through Spark project, which is about to end by 31st of March this year. So it's almost, because although the project was of initially 2 years, but because of COVID, it has been given twice extension, and ultimately it will be winding up on 31st March. So Indian Institute of Technology, these are autonomous institutions governed by Government of India, public funded institution. There are many in numbers, almost 22 in numbers. Many of them has been recently established, but ours has been the initial ones of the IITs. So IIT Roorkee was established not as an IIT, rather Thomson College of Engineering by Britishers when India was under colonial rule 175 years ago. And it is oldest engineering college in India, one of the institute of national importance, and it's a dream academic destination among the students. Originally established in 1847 as Thomson College of Engineering, and later on it was given the status of university after we got independence, and in 2001 it was given the status of Indian Institute of Technology. So we have 23 departments, 3 center of excellence, 1 school, 520 plus faculty members, 9,500 plus students, out of which 50% are undergraduate, 25% postgraduate, and 25% PhD students. Our campus is fully residential for student as well as faculty. And we have 2 satellite campuses. One is in Noida, which is in the National Capital Region of Delhi, and another one is nearby to Roorkee. So, coming to our global collaboration and student scholar mobility, 100 plus countries from where students have been educated, 250 plus international students are studying presently. There are 100 plus MOUs with foreign universities, and in fact with Queen's University, our institute has recently signed the MOU, I think few weeks before. There are 560 plus research and consultancy projects, 470 plus global agencies and clients, 148 plus sponsored research projects, and 250 plus patents files and granted. We have global collaboration footprints. The institute motto is collaboration, not competition. So, this is ranking as per the different ranking agencies, 5th in India in terms of innovation achievements, and then selected twice as RO as one of the most innovative institute in India by Confederation of Indian Industries. Then first in architecture in India, 6th and 7th overall in the NIRF ranking, which is ranking by Government of India, and 369th rank in the QS World ranking. So, I'll quickly cover these things. Here are some of the excellence here. Recently, we have a data science and AI center has been set up. 7 new academic programs has been incorporated. There is a center for drone research which has come up. Space technology cell has also recently come up, and yeah. So, there is an acute focus on flow of talent to create global knowledge partnership and promote innovation. We have joint dual degree programs with foreign institute where say for example joint doctor degree program where few semesters student do their research work in the foreign university, and few semesters they do in IIT Roorkee, and the degree is awarded jointly. So, one of our such agreement is there with University of Alberta, which is going on since last so many years. Dual award degree and joint supervision in project, dissertation and thesis, this is also done. We have joint international projects through various initiatives of Government of India. There is a faculty exchange initiative. There are various programs, in fact, International Science and Technology Cooperation, then scheme for promotion of academic and research collaboration, SPARC. This is the scheme under which I am visiting here, and we have been awarded the project. There is other scheme, visiting advanced joint research, which they call it as Vajra. There is global initiative of academic network, GYAN, which is essentially conducting of short-term courses with the cooperation with the foreign faculty, and there is a scheme with the Asian countries as well. We have international network, Duo India fellowship programs are there, DST Africa Initiative, Shastri India Canada Institute, it's again fellowship very popular among the students. IC Impact, then SATU President's Forum for South Asia and Taiwan Universities, United States India Education Foundation, Japan Society for Promotion of Science, and so many. Visiting faculty at IIT Roorkee, we appoint foreign faculty for a fixed tenure of up to 5 years, and appointment is being done as visiting professor, associate professor or assistant professor, and it's available up to 3 years, and nominations can be made by head of department or faculty member of the institute. Here are some of the innovation activities which are there in our institute. There is a Rethink Innovation Lab is there, then there are technology incubators. I have Divya Sampark. If you have a company out of any idea of the student or faculty, then there are smart city projects. There is a Param Ganga supercomputer which has been recently established. There is a technology innovation and development of entrepreneurship support business incubator which provides funding to the student and faculty. So we have a vibrant and vivacious campus life. In fact, Professor Lee has been part of one of such activity, because when he visited us, there was a student cultural program was going on for 3-4 days. So we have a very vibrant. There are many student activities for such as artificial intelligence and electronic society, model and robotics section, and so on. Yeah. So IITR honestly look forward to further strengthen our global cooperation in the field of research and innovation. So this is all about IIT Roorkee. I'll quickly just give you a brief about our activities, and then I'll move on to our presentation. Yeah. So robotics and control lab, I'm heading that lab since 2006 over there. We have international collaboration with many of the institutes across the globe. In Asia, with Kanpur National University, we had 2 3-year projects on the hyper redundant robot and the walking robot. Then in Europe, we have collaboration with France University of Lille, and we worked on the mobile cooperative bionic robot. In South America, we have had collaboration with University of Nacional de Rosario on the hybrid manipulator. With Queen's University, we are working on design of cable driven parallel robot, and we have been recently awarded 2 more projects with the US universities. University of California, Irvine on UAV for mining application, and with Old Dominion University, Norfolk, Virginia on UAV for flood estimation. So our research work varied. We work on the varied topic under robotics, such as space robot, quadruped mobile manipulator, to name a few. We have recently added up topic of construction robotics and soft robotics in our area, and we are venturing into machine learning and AI application in robotics. So these are some of the earlier work which we have completed. These are part of the different research projects. That is walking robot with compliant legs. We developed one and tested here. Then the wire actuated hybrid, there is a robot, hybrid robot for bomb detection and disposal, basically, which was developed by the Defense Research Institute, and they wanted us to explore the possibility of the wire actuation of the joints, because currently they are using the motors and it becomes very heavy. That is, the arm load has increased a lot. So they wanted some wire actuation. So we worked on that. Then mobile robot with manipulator. This was the project which we did with Argentina. There was a space robot project. Initially, we have been granted. Then one on the miniature robot for endoscopic surgery for biopsy sample collection. So this also we worked upon. So this is the surgical robot setup which we did recently. My PhD student completed this one work where we tested the miniature robot on a chicken tissue. This is the work which we did with the University of Lille in the France on the bionic manipulator. because these are basically the continuous manipulator which have infinite degrees of freedom, and accurate dynamic model can help in the control methods basically. So, we try to create a dynamic model as accurate as it can be for that purpose. Then this is the work which we are currently doing, pneumatically actuated continuum manipulator. Basically this bionic manipulator is pneumatically actuated. So, it has got severe limitation on the payload capability. It cannot carry lot of payload. So, we try to overcome that with the help of wire actuation of the continuum manipulator. So, this is another PhD student who was working, sorry. This is the hyper redundant soft robot. This is the work with the South Korean university which we are currently doing. This we did the dynamic simulation of that, and then we tested a prototype where we developed a unique pneumatic actuator here for the serpentine motion of the board. And then we worked on the drone with the aim of putting that hyper redundant manipulator on the drone. So, we did modeling, dynamic modeling and simulation of the drone here. It is H type of quadcopter. This is another work which was done by one of my PhD student who works in the building research. So, here we developed a robot prototype for the inspection of high rise building having both metallic and non-metallic structure. So, this was so for the metallic structure we worked using the magnetic type of adhesion, whereas for non-metallic we worked on the suction type of adhesion. So, our construction robot activity started with the serial type of manipulator, actually initially for bricklaying purpose. So, we did initially some work on this and then proposed this for a high rise building, of course, not very high rise up to say second or third floor. And then this is the work which we are doing with Professor Lee and Professor Laila, cable driven construction robot. So, this is what we conceptualized it. Maybe I will talking more about in my lecture. And for this we carried out the simulation and the experimental studies. This entire experimental setup was prepared in house in our lab, which is in full working condition currently. This is the work of one of my other PhD student who is working on path planning of omnidirectional mobile platform using ROS navigation stacks, where in the home environment we want to plan for the mobile robot so that it can avoid the static as well as the dynamic obstacle in reaching from one room to another room. And this is about the startup. We have come up with a contactless medical registration device, TARA basically, and during pre-COVID COVID period we worked on it, and which has now taken shape of a startup, and recently it is going to be deployed in the hospital in Roorkee, and it's especially helpful when there are long queues in the hospital. So, multiple deployment of this device can lead to the lesser registration time. So, with this I complete my lab introduction, and next I will talk about the work which we have done on this one, that is design and development of cable driven parallel robot for additive construction. Although it is a work of my PhD student which spanned almost 5 years, but I will just try to give you the glimpse of what we actually did, and leading to the experimental development of the experimental bot. So, before I start, I would like to acknowledge Ishan Chawla, the PhD student at Roorkee, who worked on this project. In fact, he visited Queens for 6 months also. He was here in this campus as part of his visit as part of the project. Professor Laila, Professor Lee, and my other colleagues, Professor Samantre from IIT Kharagpur, who was co-principal investigator, and Professor U.K. Sharma, who is from the civil background, and he helped us in conceptualization many of the things. So, conventional construction is basically, as you know, it's slow, waste prone, costly. It has got limited architectural freedom and hazardous to labor. So, people thought of doing some sort of automation into it, bringing some sort of automation. So, the concept of brick laying came. There is a company in US basically. They developed, used a serial manipulator basically for brick laying purpose and applying of the mortar on the brick. So, it is a time saving, can work in hazardous environment, can be cost effective. There could be some architectural freedom and labor safety is also possible here. So, if we think about the possible solution for the use of robotics in construction, there could be 3 probabilities. One is the serial robot, other is the gantry one, and the third one is the cable driven parallel robot. If we look for the serial robot, so this is how the serial robot can be used for the say printing of a house, but because it has got a fixed base, naturally the workspace is going to be smaller. And if you want to make the base mobile, then naturally you need a smooth terrain for the mobile to move. So, mobile serial robot require proper floor for mobility, and again there are issues with how to pass through the doors or the opening which are going to be in the house. The other solution is the gantry robot, but it has got again limitation as limited workspace, heavy structure. It is basically a type of Cartesian manipulator, and it required very high torque actuators, and of course, when you want to shift it from one location to another location, there are problems. So, it is difficult to transport and install. The solution which I am going to talk about is the cable driven parallel robot. It can cater a larger workspace, and it is easy to transport because we are using cables, easy to disassemble and reassemble, and it is relatively inexpensive. So, coming to the terminologies of this cable driven parallel robot, we can see that it essentially has got a mobile platform where we could have the concrete mixture, okay, from where the mixture could be poured into, and this mobile platform can be driven by the multiple cables basically, which are attached to the actuators, or that is attached to the motors. Okay. So, here the parallel robot in which cables are used instead of the rigid link, that is why we call it as the cable driven parallel robot. There are very key features of it, and that is the high payload to weight ratio. We can carry larger payload over here, that is the mobile platform can have a lot of concrete mixture into it. There is a larger workspace possible. So, you can think of building say 2-bedroom or 3-bedroom houses, easy to transport, easy to assemble and disassemble, and relatively inexpensive. It is not that the concept of cable driven parallel robot is new. Okay. The cable driven parallel robots are there, but in the different applications. For example, in the stadium camera, you can see that it zooms from one location to another location. Then large scale motion simulators also people have been using it, high speed operations, and in fact in the telescope also it has been used. So, when we conceptualize this project proposal, so this is how we conceptualize this, that we could have a mobile platform over here which could be hanged through cables which are guided through pulleys and actuated at the end with the help of motors, and the mixture could be pumped into from the concrete mixture over here, and these pulleys could be guided through a frame. Basically, they could be attached on the frame and it could be guided, and the house design can be kept as a say solid model or whatever design you want, that you can keep in the model, and then this design, the trajectory for this design to follow could be generated, and yes, concrete can be poured here. The only limitation in this one which we felt was that the time taken for the curing, okay, because one cannot deposit the concrete of greater height, otherwise it bulges. So, there is literature on the cable driven parallel robot available. One could be a configuration of suspended cable driven parallel robot like this, suspended through wires. So, here since it is suspended, there is no issue of the cable collision with the printed structure, but since it is suspended, there is low stiffness in the Z direction, vertical direction. Then we could have the over constant cable driven parallel robot. Many times what we do actually is that to make the structure stiffer, we provide multiple number of cables, okay. But when you provide multiple number of cables, what happens that we try to make the structure over constrained. So, that happens, plus since we are using multiple number of cables, what problem happens that many times those cable start obstructing the structure which you have already created. So, again that causes a problem. Then we could have, so a solution to this problem could be a reconfigurable cable driven parallel robot, where we can move the lower anchor points, okay. We can move the lower anchor point when they start obstructing the already made structure, okay. But it require additional actuators and sensors. So, when we looked at literature on kinematic analysis, there are different type of cable model which exist in literature. One is the ideal cable, basically where we assume that cable are massless and inelastic, say like this. Or we could have the elastic cable model are also there, where we say that the cable is massless, but there is certain elasticity in the cable. And the catenary cable model, where we say that the cable have mass and also they are elastic. So, this is the most generalized, but again we have challenges here. The first case is mostly used, it is easiest because we assume that the cable are massless and inelastic. For the small scale robot, this assumption is valid, and the closed form inverse kinematic solution are possible. Inverse kinematic solution in the sense that for the given position and orientation of the mobile platform, we could find out the length of the cable, how much length I have to extract or I have to release for that purpose. So, the inverse kinematic closed form solutions are possible, and the forward kinematics is solved numerically or using neural network for this ideal cable. Coming to the elastic cable, medium scale robots with significant acceleration are there. Kinematic is coupled with elastic statics here. and both inverse kinematic as well as the forward kinematics are relatively complex, but can be solved in real time using numerical algorithm. And for the catenary one, as I said, these are used for the large scale robot with significant cable mass and elasticity. Limited literature is present in this case. Kinematics is coupled with statics, and both inverse kinematic and forward kinematic problem are significantly complex and are difficult to solve in the real time. So, our objective of the work has been in-depth kineto-static analysis of a redundant over constraint cable driven parallel robot considering cable mass and elasticity, finding a computationally efficient alternative to solving kineto-static problem in the real time, analysis of the workspace and optimal design of over constraint cable driven parallel robot for concrete printing application, comprehensive dynamic model also, although if you are moving your bot at a slower speed, dynamics is not that important, but if you move it at greater speed, then one need to have idea about the comprehensive dynamic. So, we try to do the comprehensive dynamic modeling considering cable mass, elasticity, flexural stiffness and flexural damping all together. Then the design of reconfigurable cable driven parallel robot requiring a smaller or less actuator for application in concrete printing. And then the last aim was the hardware design and development of over constraint cable driven parallel robot for concrete printing application. So, so if I some of the term I have already explained to you. So, let me just explain briefly the other terms which I may be often talking here. Say this is my moving platform which I have been talking about. These are say L1, L2, L3, L4 are the lengths of the cables basically which manipulate this mobile platform, and these are the actuators. Okay. So, the inverse kinematic means that for the given position and orientation of the mobile platform, say this is my inertial coordinate system, and the position of the mobile platform CG position is given by vector r basically, and the orientation I can represent with help of the rotation matrix. So, for given r and r, small r and capital R, when I am interested in finding out these cable lengths, this is what we call as the inverse kinematics. The forward kinematics is the reverse, that is you are given all these 4 cable lengths, and I am interested in finding out the position and orientation of the mobile platform, that is the forward kinematics in this case. Inverse kineto-static means that for you are given the position and orientation of the platform as well as the forces and moments acting on the platform, that is also given, and you are interested in finding out the cable lengths as well as the tension in the cable. Okay. So, that is what we call as the inverse kineto-static problem. Then similarly, we have the forward kineto-static problem where we are given the cable length and we are given the force and moments acting on the platform, and again we are interested in finding out the position and orientation of the mobile platform and the tension in the cables. And if we talk about just simple static analysis, I am interested in finding out that if certain force and moments are acting in the platform, what are my tension in the cables are going to be. So, I will be talking about few words only. So, first one is the kineto-static analysis of redundant cable driven parallel robot considering cable mass and elasticity. We targeted a gap that limited work on the multiplicity of the kineto-static solution of a redundant cable driven parallel robot is reported. So, if we look at the inverse kinematics of the massless cable basically, so we could find out here mathematically the length of the cable as say here, it is a simple vector addition basically. So, the position of the mobile platform given by R and orientation by capital R. This is the location of the point where the cable is fixed into the mobile platform, say by represented by vector bi, and this is the length of the cable, and this is the anchor point basically given by ai. So, I can find out this LMI. And if I assume that the cables are elastic, then unstrained length of the cable I can find out using this LMI and considering the elasticity and tension in the cable and the cross section area of the cable. The statistics considering massless cable basically is composed of the cable tensions which is multiplied by a wrench matrix and the forces and moments acting at the mobile platform. So, this way we can consider the statistics, and as I said, the over constant robot number of cables are larger than the degrees of freedom of the robot. So, basically number of cables NC is going to be greater than the number of degrees of freedom of the robot. If we talk about wrench feasible workspace, we can define that by this matrix basically W R R into that tension in the cables vector plus the forces acting on the mobile platform, and of course, these tensions are within a certain range, a minimum and maximum value. Basically, the maximum bound is considered considering the actuator limitation and breaking load of the cable, and the minimum bound is considering unilateral tension constant, slackness, vibration, cable slip and all. This is the catenary cable model. Basically, we can talk about the position x, y, z here for given the forces at the free end and at the fixed end. So, once that is done, we can carry out the kineto-static analysis of this basically by writing the force and moment balance equations over here. So, basically the forces acting on the cable and on the platform. So, we could find out the cable endpoint must satisfy this nonlinear kinematic constraint basically. So, so here comes these forces acting at the free end basically, and then we try to work on the constraint optimization problem for this case. If say NC there are NC number of cables and the n degree of freedom robot is there. So, number of unknowns are naturally going to be 3 times NC and number of equations are 3 NC plus n, and these are the considerations or conditions which I explained for the under constraint, minimally constraint and the over constraint, where your number of cables are going to be more than this number of degrees of freedom. So, for over constant robot, number of unknowns are larger than number of equations. Multiple solutions can be possible for a given pose. So, a unique solution can be obtained using constraint optimization. A unique solution is obtained by minimizing a specified cost function. Kinematic and static equation will act as constraint to the optimization, and tension constraints are also added. So, we proposed some selection criteria over here to take care of those constraints. So, one is the minimizing the tension in the cable, and of course, these selection criteria is valid if you need to have low energy consumption, low stiffness and large sagging, suitable for application where compliant mobile platform with energy solution is desirable, okay, such as human interactive logistic. Then the other criteria could be minimize the deviation from the mean tension, Of course, it has moderate energy consumption, moderate stiffness and moderate sagging, and it provides continuous and smooth kineto-static solution. Then maximizing the tension in the cable, basically for high energy consumption, high stiffness, and of course, suitable for applications such as cable driven 3D printer, cable driven telescope and all. So, we carried out the simulation for this for the planar case, basically 3 degree of freedom cable driven parallel robot. So, the 3 degree of freedom of the mobile platform, basically it means that 2 Cartesian motion x and say z and 1 rotation, this one. So, we considered say that this is actuated by 4 cables. So, here are some of the animation results as per those 3 selection criteria. Selection criteria 1, 2 and 3 for a 8 type of motion of the mobile platform. Then we looked at the catenary versus massless cable model. Although the difference are well known, but from the technical point of view, in catenary cable model, kinematics is coupled with statistics, and in massless cable model, kinematic and statics are decoupled. This is non-linear in nature, this is linear in nature, and this is solved using numerical or optimization method, and here it is kinematics can be solved analytically. Statistics is solved numerically, but problem is relatively simple, and yes, it is difficult to employ in real time application, and this one is easy to implement in real time application. So, error in massless rigid cable lengths, then we carried out this analysis for the 2 of the I mean the results we plotted for the 2 of the cables as per all those 3 selection criteria here. So, this was for the cable 1 and this was for the cable 3, how much is the maximum error. So, this is error in massless rigid cable length. Then we looked in the error in the massless rigid cable length. Then here we looked at the massless rigid elastic cable tension, how much error is going to be. Of course, we took various type of cables, basically Dyneema 5 mm, Dyneema 8 mm, Dyneema 10 mm and all. And then we tried to look at alternative to catenary cable model, basically. What could be done on that, and then we carried out this spatial cable driven parallel robot animation for a circular trajectory here from the top. Next work we did on the workspace analysis, because workspace is really one of the challenge here, because initially the you get a larger width, but as the height increases the width keep on reducing. So, we carried out workspace analysis and design of this one, considering cable mass and mobile platform orientation, and we found out that there is a substantial improvement in the workspace area when we are considering the mobile platform orientation also. So, here we carried out selection criteria first for minimizing of the cable tension and minimizing of the cable sagging. So, these 2 criteria we considered. Then we try to find out the range feasible printable workspace analysis. So, this is what I have been talking about basically. Initially you get a greater width, but as your height increases your width keep on reducing, and as I said, if we do not consider the orientation of the platform, then your workspace is smaller, whereas with orientation you get a little larger workspace. Okay. So, this is how it is demonstrated through a schematic for a planar motion. Then we carried out a comprehensive dynamic model of the cable driven parallel robot, and for this comprehensive dynamic model, basically we tried to model the cable. So, cable we tried to model that cable is having a stiffness and damping in the transversal direction, as well as to take care of the twist in the cable, we considered the torsional stiffness as well as torsional damping also, as you can see over here. And to take care of the cable mass, we lumped that mass parameter over a definite segment. Okay. So, this is how we did. So, cable is modeled at series of spring mass damper system connected by a revolute joint. Each revolute joint have a stiffness and damping to take care about the bending, stiffness and damping of the cable. These are the stiffness relationship which are essentially found in mechanics of material textbook. So, for translational stiffness and damping and the torsional stiffness and damping. Yes, this is the bond graph. I do not know how many of you are aware of it. In fact, yesterday I took a workshop on this one, the bond graph modeling. So, we created a dynamic model using this bond graph for this system, and so we require essentially the velocity relationship. So, the velocity of the cable basically, so we could find out mathematically for the translational velocity and the angular velocities, we could find out here by x, knowing x and z coordinates and x and z velocities. Then we can create the dynamic model of it, and we created a cable pulley interaction here basically. So, again making a contact and non-contact depending on how the cables are touching the pulleys basically. So, the stiffness and stiffness and damping model basically. So, as a force we applied whatever force are being generated when the cable is coming in contact with the pulleys. And yes, this is how cable driven robot we model. Of course, this is very simple relationship. The position is R plus R into BI basically, where R is the rotation matrix and BI is this vector, this is the rotation matrix. So, we could find from position of this cable, we could take a derivative of it, we could find out the velocity, and then we could create a model here. So, various sub models of the different cables over here, and here is the model for the mobile platform, where we considered the translational motion as well as the rotational motion of the mobile platform, and then these mobile platform motions are connected through the cables. So, here comes the simulation result. The free end of both the cables is pulled downward to achieve the circular motion of the mobile platform. Say this is the reference trajectory which we gave, and the cable velocity at the free end is obtained by using inverse kinematic for the ideal cable case that we did, and we simulated for the two cases 2 degree of freedom cable driven parallel robot with a point mass of say 10 kg and 3 degree of freedom cable driven parallel robot rectangular mobile platform, because we wanted to consider the orientation also here, and we considered a mass of 2.5 kg. So, these are the results basically for the different time interval. This is for the 3 degree of freedom cable driven parallel robot. For the circular trajectory, these are the errors, and this is the animation basically which you can see. Here you can see that the orientation of the mobile platform is also changing, and this is how the interaction of the cable and the pulley which has been modeled. So, these wires are basically pulled, so that this mobile platform has got a circular trajectory to follow. We validated this model, the bond graph model, using this catenary cable model basically through animation. So, that you can see the proposed one and the catenary cable model. And the last part of my presentation is on the design of this robot, prototyping of this robot, that is the cost efficient design and development of cable driven parallel robot for concrete printing. So, this is how our structure looks like. This is the mobile platform where the concrete is fed through a funnel over here. We have a screw to turn to mix the concrete over here, and this platform is pulled through these cables, and these cables are actuated through motors over here. So, this is the winch and this is the mobile platform which we designed, and these are the panning pulleys over here. This is the controller design which we carried out. It consisted of essentially a SMPS Arduino controller we used, motor driver and the motor over here. So, this is the closed loop control basically through encoder. We converted the count conversion was carried out and reference count was given, then we used the PID controller and through which we gave the PWM to the DC motors. So, this is the schematic basically. The motor drivers were here, one was the master and others slave. So, this is how we generated the trajectory generation for the concrete printing. The CAD model of the building, that we got the STL file. So, we fed that STL file to the slicing software to get the G code, and then this G code was given to the host software through COM port. It went to the 3D printer firmware, from where we got the XYZ positions, and through inverse kinematics we could get those the rotation of the motors. So, we carried out this cost analysis basically for making of this one, and this is the setup basically, and here are the error in the platform position. So, this is the setup which you can see which we developed. So, initially we tested with the circular trajectory here, as you can see. Then a dry run, we carried out dry run before the printing. So, this was the printing with concrete. We had many failures actually. We were not sure about what should be the ratio here, mixture ratio. So, this was the concrete printing. Then we tried printing with the clay also. Again here the moisture was an issue. Initially we could not, we did not know about the exact moisture content, water content on the clay, but later after several trials we could figure it out. So, the boys were very interested to print anything. So, they just print IIT Roorkee. So, these are various failure and successes of our journey. To conclude, multiplicity of solution is a great challenge basically, and one can exploit to choose a unique solution such that error using massless, rigid or elastic cable can be reduced. Massless cable assumptions overestimates the printable, and choice of selection criteria significantly affect the printable workspace. Considering platform orientation leads to improvement in the printable workspace, as I discussed. Significant error in the mobile platform trajectory using inverse kinematics for ideal cable shows the importance of the proposed comprehensive dynamic model, and proposed design approach can be utilized in developing cost effective cable driven parallel robot for additive construction. If we look for the future ahead of this, we felt that when we were modeling the interaction between the cable and the pulleys, there were many if else loops were used just to check every time whether it is in contact or not in contact. One need to find out some solution for that, because it significantly reduces the simulation speed. The dynamics and control can be improved further by considering elastic cable and pulley dynamics. Calibration routine of developed cable driven parallel robot can be improved using limit switches, and control of fast moving cable driven parallel robot with significant cable mass can be explored in the future. So, this could be the future perspective rather than using of the pillars to hang the mobile platform. Adjacent structures can be used to hang the mobile platform, and the printing can be carried out. So, these are some of the very few references which one can look into, and with this I would like to thank you all for giving a very patiently hearing me over last an hour.